Hi guys, we're going to talk about ideal versus real gases. So of course all gases are real, but we do call some gases ideal if they behave according to the kinetic molecular theory. So if you remember, KMT had 6 statements, and based on kinetic molecular theory you came up with PV equals nRT. And so if a gas behaves according to KMT and the assumptions that KMT makes, we say that it's ideal. If it's ideal, that also means that PV equals nRT is a good equation to use. So for example, if I am given the pressure and the amount and the temperature, I can use PV equals nRT to solve for the volume, and I will get a pretty accurate answer, a very precise answer, as long as the gas behaves ideally, again meaning that it follows KMT with its assumptions. If the gas does not behave ideally, meaning that one of those assumptions in KMT fails, then when I plug in my values for P, N, and T and solve for V, I will get a value that is not very close to reality, not very accurate. So the more ideal it is, the more it behaves according to KMT and its assumptions, and the more accurate my values will be when I'm solving using PV equals nRT. The less ideal it is, meaning that the more the gas does not behave according to the assumptions that KMT makes, then the farther away from reality my values will be when I do my calculations. So kinetic molecular theory does make several assumptions, 2 main assumptions really. And so let's talk about those 2 assumptions and when would they fail. So here are the 2 assumptions that kinetic molecular theory makes. The first assumption is that the gas particles are so small and the spaces between them are so large that the volume of the gas particles themselves is negligible. So when we plug in V into PV equals nRT, we're plugging in the volume of the container. We're not really looking at the volume of the gas particles themselves. So whether it's CO2 or helium or neon, as long as it's in a 2-liter container, we just plug in 2 liters for the volume. The second assumption is that kinetic molecular theory assumes that gas particles have no intermolecular forces between the gas particles. So there are no attractions between the particles. Now, most of the time that's okay to make that assumption because the particles are so far apart, so the attraction is not really significant, but there are times when that fails. So these are the 2 assumptions. Gas particles have no volume for the particles themselves, and then gas particles have no attraction or IMFs between the particles. So let's address the first assumption, that gas particles have no volume. In reality, of course gas particles have volume. So let's take a look at if we have a container with some gas particles. So let's take a look at this container here. So it has some gas particles in it. The gas particles are really small and the container is relatively large. So we can assume that the volume that's taken up by these gas particles is equal to the volume of the container. So that's what we plug it in here, is the volume of the container. Now let's take a look at this container here. It's a smaller container. So when the volume of the container itself is small, or when the gas particles themselves are relatively large, this assumption fails. Because in reality, if you look at this gas particle, the volume that it has in order to move is equal to this container minus the volume of this gas particle. Now again, if you're looking at a large container with small gas particles, you can ignore that. The volume that this particle moves in, yes, is equal to the container minus these, but these are really negligible compared to the volume of the container. But if you look at a small container, or the gas particles themselves are really large, then that assumption fails. And when we plug the volume of the container in for V, that's not going to give us a very good answer. So to fix that, if our volume of container is really small, or if our gas particles are really big, instead of V in PV equals nRT, we plug in V minus B times N. That is really the volume that gas particles have room to move in. The V being the volume of the container. B is a constant. It depends on each gas. Each gas has a different constant. The larger the gas particles, the larger that constant. And then N is the number of moles, the number of moles of gas particles there. So you take the volume of the container minus a constant times how many gas particles there are to fix that problem. The second assumption that KMT makes is that gas particles have no attractive forces, no intermolecular forces between each other. Now, under most conditions, again, that's an okay assumption to make, but there are some times when that fails. In instances when there is high pressure or low temperatures. The reason for that is because if you have high pressure, that means the particles are colliding all the time. And so if they're colliding all the time, that means that they're spending a lot of time next to each other. And so when they're next to each other, then those intermolecular forces become significant. Also at low temperatures, this assumption fails. So under regular, a normal temperature or a high temperature, particles are moving really, really fast. And so they slide by each other very, very fast, and so they don't meet each other for very long. But at low temperatures, that means the particles are moving very slow, and so if they're moving very slow, again, they are close to each other for longer periods of time, and so whenever they're close to each other, then the intermolecular forces become significant. Now, the intermolecular forces affect the pressure. The more intermolecular forces, the more pressure there will be. So, when we have an ideal gas that has very, very weak intermolecular forces, or the temperature is really high and the pressure is really low, where we don't have significant intermolecular forces, if we use PV equals nRT, then it works fine. But if it is under high pressure or low temperature, or the attractions between the particles are really, really significant, then this does not work anymore. And so to fix that, instead of just B, we put P plus A times N over V squared. So P is the regular pressure that we would normally plug in. A is another constant, and it's different for each gas. The stronger the attractions between the particles, the higher A is. N is the number of moles, and V is the volume of the container. Okay, so let's take a look at neon versus hydrochloric acid. Both of these are gases at room temperature, and we want to know which one behaves more ideally. So, ideal gases are ones that follow KMT with its two assumptions. Remember, the two assumptions are that gas particles have no volume and that gas particles have no intermolecular forces, those two. So, the one that will behave more ideally is one that will give you very small volume. So gas particles are really small because we're saying they have no volume. So the smaller their volume is, the more closer to that assumption it is. And then also KMT says particles have no attractive forces, intermolecular forces. So the one with weaker intermolecular forces will be the one that behaves more ideally. So the one that behaves more ideally is always the one with smaller volume and weaker intermolecular forces. And so in this case, neon would be the one that has both of those. So neon would be more ideal. So we had said that to fix these assumptions, in case, a gas does not behave very ideally, if it behaves like a real gas, to fix that, we plug in this expression for the pressure and this expression for the volume into PV equals nRT. If we do that, then we get this big equation. This is called the van der Waals equation. You need to be able to use the van der Waals equation. You don't have to memorize it. It's going to be on the test for you, but not in that question. So if you flip through the test, you will find that equation given to you somewhere. So you do not really need to memorize it. Just look for it in the test somewhere. But you will need to use it. So let's look at an example where we would use that. So this example says, use the van der Waals equation to calculate the temperature of 3.6 moles of nitrogen gas in a 4.6 liter cylinder at 2.5 atm if A and B for nitrogen are given to you respectively. So they will always give you the values for your constants A and B. Now what I would like you to do is to calculate it using the ideal gas law, so PV equals nRT, and then also use the van der Waals equation, which is the real gas law. Okay, so let's do that. So we're going to do PV equals nRT. So our pressure is 2.5 atm. Volume is 4.6 liters. N is 3.6 moles. R, if we're using ATM, would be 0.0821. ATM times liters per mole Kelvin. And then T is what we're solving for. We're also going to do that with the van der Waals equation, which says B plus AN over V squared. So the whole quantities are P. Then that is times V minus BN equals nRT. So, here are my numbers plugged into the van der Waals equation. And I actually don't have a calculator with me right now at home, but if you calculate T from here and T from here, you will find that they are relatively different numbers. So the more accurate one will be the one from the van der Waals equation. It's just a lot of work, as you can see. And so most of the time, if a gas behaves pretty ideally, then we just use PV equals nRT to, approximate the value. And it's usually pretty close to reality. So let's summarize what we just talked about and what are some questions that could show up on the test. So first, I could ask you, what are the two assumptions that KMT makes? And so you tell me that gas particles have no volume and gas particles have no intermolecular forces. Another question could be, which gas behaves more ideally, like the question with the neon and the HCl, for example. So the one that behaves more ideally will be the one that has smaller particles in volume and also weaker intermolecular forces. If I ask you which one behaves less ideally, then it would be the one with larger particles and stronger intermolecular forces. And just to review the intermolecular forces, if you remember, hydrogen bonding was the strongest, followed by dipole, and then the weakest would be London dispersion. Another question I could ask you is use the van der Waals equation to calculate either the temperature or the pressure or the volume or the amount. If it does not specifically tell you use the van der Waals equation, then you use PV equals nRT. But if it specifically says that, then you have to use the equation. And again, it will be somewhere for you there on the test. Another question I could ask you is, what are the conditions under which KMT fails, or PV equals nRT fail? And so there are three conditions. Either when you have small volume of container, and so that's because the volume of the gas particles then would become significant, or under very high pressures, because that means there are lots of collisions, and so the gas particles are spending more time together, and so the intermolecular forces are significant, or under very low temperatures, because that means the particles are moving very slowly, and so again, they are next to each other for a longer period of time, and so the intermolecular forces then become significant. All right, that is it for ideal versus real gases.